Hello students, your Saurin sir is back once again and we are still on with electrophilic substitution reaction. In the previous episodes, we have come across different electrophilic substitution reactions like nitration of benzene, sulfonation of benzene, halogenation of benzene. In that we have already included the chlorination and bromination reactions of benzene. So today we will take the fourth type of electrophilic substitution reaction of benzene, and that is alkylation reaction of benzene. Alkylation reaction of benzene is also known by the name of the scientists who have worked upon this type of reaction. They are Friedle and Craft, and so the reaction is also known as Friedle-Craft's alkylation reaction. Let us see how the reaction goes on. As you know, we are talking for the reaction of benzene, so we have taken C6H6, the molecular formula of benzene. We are going to perform the alkylation reaction of benzene. And alkylation means you need an alkyl group. Alkyl group means it may be in the form of methyl group, it may be in the form of ethyl group. In short, any alkyl group, when carried on for the reaction, it is known as alkylation reaction. Here we will take methyl CH3Cl, methyl chloride, that is alkyl halide, over here for the alkylation reaction. And for that, again, you know, we are on with electrophilic substitution reaction. So we are going to generate the alkyl group in the form of electrophile in such a way that this CH3 attains the positive charge, because an electrophile is a species which attains a plus charge, which is considered to be lacking electron. So to make our studies very accurate, very clear, we need to have CH3 with the plus sign, and for that we need to choose a specific precise reagent which will later on act as a catalyst. The reagent chosen over here is interesting. I'll write AlCl3 as generally, in general, it is written so. But there is one characteristic point that we all should keep in mind, and that is that aluminium chloride, where aluminium is a 13th group element which has got 3 valence electrons, it straight away combines with 3 chlorine atoms. Over here you can see Cl, Cl and Cl. I have written 3 chlorine atoms. 1 chlorine atom with 7 valence electrons that I am showing you, highlighting you over here. It is sharing 1 electron with Al, and as a result you can see, if you consider the Cl atoms, every Cl atom has completed its octet. On the other hand, if you consider the chlorine atom and now aluminium atom, aluminium, after sharing its 3 valence electrons, it has now attained only 6 electrons. So you can see it is lacking 2 electrons for completion of its octet. But mind you, this is a salt which has got tendency to absorb moisture from the atmosphere. So I would say a technical word for the salt, that this salt is hygroscopic in nature. Hygroscope, having tendency to absorb moisture. So if you take only AlCl3, then the Cl that we want over here, so that CH3 can attain plus sign, will not be forming a bond with aluminium, that is a coordinate covalent bond. No, it won't form. Why? Because already aluminium is bonded with 3 chlorine and it is hygroscopic in nature. But if we clarify that this AlCl3 is anhydrous AlCl3, then this Cl being more electronegative than the carbon to which it is bonded. I'll show you over here. This is CH3 and Cl. Out of carbon and chlorine, chlorine is more electronegative, and as the reagent is anhydrous AlCl3, it will have a tendency to pull the chloride ion out of CH3Cl, so that this chloride ion will take away the electron of carbon to which it is bonded, and as a result Cl will attain a minus sign and carbon will attain a plus sign. And keep in mind, we want carbon which should attain plus sign, because we are studying electrophilic substitution, we want an electrophile. So now this Cl minus, that means it is having 1, 2, 3, 4, 5, 6, 7 and 8 electrons, gets onto aluminium over here. So I'll write for you as Cl 1, 2, 3, 4, 5, 6, 7, 8 and a minus sign. This implies that both the electrons required for octet completion on aluminium will be provided by Cl to aluminium, but finally the octet gets completed and AlCl3 now converts into AlCl4 minus. This AlCl4 minus prompts CH3 plus to attack the benzene nucleus. The whole scenario is the same as we understood in the previous episodes of nitration, sulfonation, halogenation, that benzene is rich with pi electron cloud above and below the plane of benzene, and as a result the CH3 with plus, that is lacking electron, gets attracted to the benzene nucleus, where 1H, any 1H atom on benzene leaves the carbon atom, leaving its electron there itself, and so the carbon of benzene will attain a minus sign. So it becomes easy for the methyl with plus group, methylenium ion CH3 plus to attack the carbon, and as a result this CH3 plus, an electrophile, attacks the carbon of benzene having minus charge, and that forms a bond with carbon, giving you a new compound named as toluene, T-O-L-U-E-N-E, toluene, or you can also name it as methyl, as this is the methyl group on benzene, so you can name it as methyl benzene. So this is how toluene or methyl benzene is generated. The concept of the reaction, that is electrophilic substitution, has been the same. Now what happens? The H which has left the carbon has attained plus charge. That H plus combines with Cl4 minus, and as a result that H plus takes away one Cl minus. Which Cl minus? The one which formed a coordinate which was sharing both the electrons with aluminium. That Cl minus combines with H plus, and that forms a byproduct HCl. And now one Cl minus is gone, you are back with AlCl3. So here I say that anhydrous AlCl3 will act as a catalyst, and it is obtained back once the reaction is over. Now earlier I said that this is the reaction also named as Friedle-Craft's alkylation. The reason of utilizing anhydrous AlCl3 in the reaction was introduced by Friedle-Craft, and that's why the reaction is also known as FC, that is Friedle-Craft alkylation reaction. The overall reaction occurs at 80 degrees Celsius temperature. If you are studying the things in Kelvin, it's simple, you just add 273 to the temperature in Celsius and it will convert into Kelvin. So other way around I can also say that it occurs at 353 Kelvin temperature. So either it's in Celsius or Kelvin, you can actually understand the units and accordingly you can adjust the temperatures. Fine. So this is how you are getting toluene from benzene. I think this is clear to you now. Fine. Okay. Instead of methyl chloride, You can also go with ethyl chloride, C2H5Cl. That is ethyl chloride. The reaction is the same. The mechanism also remains the same. And this ethyl group over here, instead of methyl group, that is CH3, you will substitute C2H5, and the compound is now known as ethyl benzene. Fine. So this is how you can get an alkyl benzene in the form of alkyl. You can take methyl, you can take ethyl on benzene, so it is also known as alkyl benzene, and the reaction is, that's why named as alkylation, given by Friedle-Craft, so it is known as Friedle-Craft's alkylation reaction. This is only one part of the reaction. I'll take the next part further from here, the alkylation of toluene or ethyl benzene, in the following episode, but keep this fundamental very clear in your mind, and as we meet in the second or the coming episode, prepare yourself thoroughly and then just join with the same. Wish you all the very best and prepare the things thoroughly. We'll get on with the next episode soon. Thank you.